Have you ever wondered how neural networks work? This question has piqued the curiosity of many, and today we're going to delve into the fascinating world of neural networks, a realm where computer science and biology intertwine. Neural networks are computational models that draw inspiration from an unlikely source, the intricate workings of our biological brain. Just as the brain is made up of interconnected neurons that communicate and learn from each other, neural networks comprise artificial neurons that have the ability to learn and make predictions, an echo of the natural world within the sphere of technology. These artificial neurons, or computational units, hold the key to the network's learning capabilities. Each neuron possesses weights and biases, with the weights acting as a form of memory that enables the network to learn, to remember, and to evolve. When we bring together many of these neurons, something truly remarkable happens. They gain the power to identify complex patterns, to discern relationships in data that might otherwise go unnoticed. This ability to see the unseen, to detect the subtle intricacies within the data, is a reflection of the human mind's capabilities. Just as our brain can identify patterns, make connections, and predict outcomes, so too can these artificial neural networks. They are a testament to the power of human creativity, a blend of biology and technology that has the potential to revolutionize the way we handle data. This, in essence, is what neural networks are all about. They are a bridge between the organic and the artificial, a tool that can learn, predict, and evolve, just like the human mind. It's a fascinating concept, one that brings together two seemingly disparate fields in a harmonious union of science and technology. So, as we delve deeper into the world of neural networks, remember this: they are not just lines of code or mathematical equations. They are a reflection of our very own minds, our ability to learn, to adapt, and to predict. This mirrors the capabilities of the human mind in a fascinating way. So, what is a neuron in a neural network, you may ask? Well, let's delve into that. A neuron, in the context of a neural network, is essentially an individual computational unit. Now, these aren't your typical units of computation like bits and bytes. No, these are a bit more complex. Each neuron is equipped with its own set of weights and biases. You can think of these weights as a sort of memory bank. It's the magic sauce that allows the network to learn. Let's break it down a bit further. Imagine you're trying to predict the weather. You could use different factors like temperature, humidity, wind speed, and so on. Each of these factors would be an input for our neuron. The neuron then multiplies each input by a corresponding weight, adds them all up along with a bias term, and passes the sum through a function to produce an output. This output can be used to make a prediction, in our case, whether it'll rain or shine. The beauty of this process is that the weights can adjust and adapt over time with more data. This is how the neuron learns. It's a bit like a detective, adjusting its hypotheses based on new clues, getting better and better at solving the mystery. Now, one neuron alone is pretty nifty, but when you start to group them together, that's when you start seeing some real computational power. Just like bricks form a house, neurons come together to form a neural network. These groupings allow the network to identify complex patterns and relationships in data, much like the human mind. This ability to learn from data, to adapt, and to identify patterns is what makes neural networks so powerful and versatile. They can be used for everything from predicting stock prices to recognizing faces in a crowd. In essence, neurons are the fundamental building blocks of a neural network. They're the individual players in the team, each learning, adapting, and working together to crack the code, solve the puzzle, and make sense of the world around us. Opening: how do we represent these concepts in C++ code? Well, let's start with the single neuron, the building block of our network. In the world of C++, we can represent this neuron with a class aptly named neuron. This class will contain three main elements. First, we have a vector of weights. These weights are the neuron's memory, allowing it to learn and adapt based on the data it processes. Think of these as the neuron's knowledge bank, storing the lessons it learns from each data input. Next, we have a bias term. This is an additional parameter that allows us to shift the activation function to the left or right, helping improve the flexibility of the model. Lastly, our neuron class needs a method to process inputs and return output. This function takes the inputs, applies the weights, adds the bias, and runs everything through the activation function to produce an output. Now, a single neuron is great, but it's when we bring them together in a network that the magic happens. To represent a full neural network, we create a new class, the neural network class. This class manages layers of neurons, organizing them into an interconnected web ready to process your data. The network is initialized based on a vector describing the layer sizes. The predict method then runs inputs through the network, layer by layer, neuron by neuron, to generate the final output. Each neuron's output becomes the input for the neurons in the next layer, and so on, until we reach the end of the network. This process is known as forward propagation, and it's how our network makes predictions based on the data it's given. And there you have it. We've translated the concepts of neurons and neural networks into C++ code. Closing. It's as simple as that, a basic neural network in C++. So, are you ready to dive deeper into the fascinating world of neural networks? Stay tuned, as we've only just begun. What should we consider when designing these networks? Designing a neural network is not a one-size-fits-all kind of thing. It's a delicate process that involves a myriad of considerations. Let's delve into some of the crucial factors. Firstly, let's talk about weights. Weights, in essence, are the memory of our network. They hold the information that allows the network to learn and adapt. The number and precision of these weights directly impact the network's representation capacity, its efficiency, and its learning capabilities. More weights mean a higher capacity for learning, but it also means a larger computational load. The precision of weights, on the other hand, determines how finely the network can tune its responses to inputs. Next, we have the architecture of the network, which includes the number of layers and neurons. This is a balancing act. More layers and neurons can provide a greater capacity to identify complex patterns and relationships in the data. However, they also increase the computational requirements and the risk of overfitting. Overfitting is when the network learns the training data too well and struggles to generalize to new information. The complexity of the data and the size of the dataset are also crucial considerations. More complex data may require a more complex network to accurately capture the underlying patterns. Similarly, larger datasets can support larger networks without overfitting, but they also require more computational resources. Available resources, including time, computational power, and memory, are also key. Neural networks can be resource-intensive, especially as they grow in size and complexity, so it's important to design networks that are within our means to train and run. In conclusion, network design is a complex process that requires careful consideration of many factors. It's about finding the right balance to achieve our goals, whether that's accuracy, efficiency, or a bit of both. These considerations are key to designing effective and efficient neural networks. Let's quickly recap what we've covered today. We embarked on an exciting journey exploring neural networks, those brilliant computational models inspired by the intricate workings of our brain. We learned how they're composed of interconnected artificial neurons, each one a computational unit with its own weights and biases. These weights, akin to a neuron's memory, enable the network to learn, evolve, and make predictions. We then delved into the fascinating world of C++ and discovered how we can encapsulate the concept of a neuron within a neuron class. This class includes a vector of weights, a bias term, and a method to process inputs and return output. To create a full-fledged network, we introduced the neural network class that manages layers of neurons, initialized based on a vector describing the layer sizes. The predict method, a key part of this class, runs inputs through the network to generate outputs. In addition to this, we touched upon the considerations that go into network design. We learned that the number and precision of weights can influence the network's representation capacity, efficiency, and learning. And the number of layers and neurons? Well, that depends on a variety of factors, including data complexity, dataset size, and the computing resources at hand. But our journey doesn't end here. We have merely scratched the surface of the intriguing world of neural networks. As we move forward, we'll delve deeper into the mechanics of these networks. We'll explore advanced concepts like backpropagation, which helps adjust the weights of the network, activation functions that determine a neuron's output, loss calculations that measure prediction errors, and optimization algorithms that help improve our network's performance. So, my friends, as we continue to build on these fundamentals, expect our networks to evolve, to become more sophisticated, more intelligent. Stay tuned as we continue building on these fundamentals and evolve our networks. And remember, don't hesitate to drop your questions in the comments below.